Hey there, this is problem set 39, applications of free energy. This is the last problem set in thermodynamics unit. Problem set 38 talked about Gibbs free energy. It was mostly conceptual though, and problem set 39 here is a lot of the maths. But one thing just to be reminded of that we talked about in problem set 38 was right here. The two ways that we can calculate delta G for a reaction. Okay, so one of the ways was that delta G of the reaction is equal to the delta G's of formation of products minus the delta G's of formation of reactants. Okay, and you got to remember that because we're using delta G naughts of formation for each thing, we're going to get our delta G of reaction at standard state, 1 atmosphere and 25 degrees Celsius. If, however, we don't want to deal with standard state temperatures, then we can use this equation, delta G equals delta H minus T delta S, which allows us to choose our temperature, and then we can get our delta H values by doing products minus reactants. Okay, and that way we can get our delta H and our delta S's from products minus reactants, plug in T, and get our G at whatever temperature we want. Okay, so you'll see that we're going to use those two methods as we do problem set 39. Oops. There you go. All right, so let's get started. So we're going to be looking up a lot of these values in the back of the book. I'm going to be using the values that are on the key, so I don't have to be flipping back and forth at the back of the book. So if some of them are a little bit different than what you see in the back of the book, that's fine. All right, let's go. So use the delta G of formation values in Appendix 4 of your book to calculate delta G of reaction, and I could say delta G naught of reaction for the combustion of diamond and determine whether it is spontaneous under standard conditions. So they don't say delta G naught, they just say standard conditions on there, same thing. So let's do this. So I'm going to get the delta G of formation for, I guess I could do this. I'll say delta G naught of the reaction equals sum of delta G of formation of products minus the sum of delta G formation of reactants. Okay, so that's going to be, and so remember that for a pure element under standard conditions, the delta G naught of formation is going to be 0. So which of these are pure elements in standard conditions? Just the oxygen. That's 0. Now, some might ask the question, well, carbon's a pure element, and it normally appears as solid carbon. That's true, but the problem says this is diamond. Standard conditions, is carbon found as diamond? No, it's found as graphite. And so because of that, this carbon is going to have a delta G of formation. So that means that delta G naught of the reaction is going to be my products, which is CO2, which is negative 394.4 kilojoules per mole, minus my reactants. I guess I could do it like this. My reactants, which is going to be 2.84 plus 0. So this should be negative. Okay, and when I do that, I get my delta G naught of reaction equals negative 397.24 kilojoules per mole of that reaction. Okay, we're not done yet. It asks determine whether it's spontaneous under standard conditions. Well, if you remember delta G of reaction, if it's spontaneous, should be negative. So this, and because this is negative, let's say this is spontaneous under standard conditions. Right? Use the thermodynamic values in Appendix 4 of your book to calculate delta G for the combustion of diamond at a temperature of 5,000 degrees and determine whether it is spontaneous at that temperature. All right, so 5,000 degrees, that means we can't just do products minus reactants, because products minus reactants gives us delta G at 25 degrees. So if we're trying to do a different temperature, we're going to have to use delta G equals delta H minus T delta S. My delta H is going to equal delta H, a formation of products, minus delta H, a formation of reactants. So let's see, CO2 is negative 393.5 minus reactants. Carbon is going to be, carbon as a diamond is 1.8 minus 0 for the pure element. That gives me units on all those values were kilojoules per mole. Okay, and now I also have, move this up, I also have that delta S of a reaction is equal to the sum of N S naught values of products minus N S naught values of reactants. So delta S of the reaction, cool, let's see. Now remember, S values are not 0 for pure elements, so I will have a value for my O2. Now I get that it comes to 6.17. And that should just be joules. Really, I should just have kilojoules because I'm multiplying each of these by 1 because their stoichiometric coefficient is 1, and that cancels out the moles. Technically, you can have kilojoules per mole, but it would be kilojoules per mole of reaction, not, but yeah, I'm just going to write joules and kilojoules there. So now I have my S and I have my H. So I can now, delta G equals delta H minus T delta S. So I could come in and plug in my H and my S. The only problem here is if I do that, I'm going to get a temperature that's something like less than 1 Kelvin, which is a problem because that's not very realistic. But, well, I guess I'm not solving for temperature, so but I will get the wrong answer if I plug these numbers in right now because this is in kilojoules and this is in joules. Okay, and so I need to change one of them, so I'm going to say, why don't I change that one to kilojoules? So I'm going to have negative 395.38 kilojoules minus 5,000 Kelvin, 0.00617 kilojoules per Kelvin. And now you can see I'm going to have kilojoules here, and then these Kelvin cancel, and I'll get kilojoules on the right side of the equation as well. Kilojoules and kilojoules, so I can subtract those. Okay, when I do that, I get my delta G equals negative 426.23 kilojoules. So is it spontaneous for graphite or for diamond to burn at 5,000 degrees Celsius? Oh, not degrees Celsius. Sorry, that was Celsius. So this needs to be 5,000 plus 273. So let me do that one more time. didn't change my answer very much. Negative 427.91 kilojoules. So is that spontaneous? Yes, because it's negative. So that's spontaneous. Let's make sure we're recording. Good. All right. So let's move on. Delta G formation values to calculate delta G for the reaction for lead carbonate and determine whether it's spontaneous under standard conditions. We're doing something very similar to what we did in 1A. So we're going to do products minus reactants. I'm just going to write products minus reactants. Now, these values, they say, look them up in the back of their book. They're actually not in the back of your book, but I have them. So likely if you did this problem, you found them somewhere else. Plug these in, and I get delta G naught for the reaction equals 43.2 kilojoules per mole. So is it spontaneous at standard conditions? Nope, because it's positive. Use the thermodynamic values in Appendix 4 to calculate delta G at 325 degrees C. I'm just going to calculate the Kelvin now because I forgot last time. Okay, and determine whether it's spontaneous at that temperature. Okay, just like we did last time, here we're going to have to get delta H and delta S. So, products minus my reactant and delta S of the reaction my two products minus my reactant gives me a delta H value of 88.3 and my enthalpy values were in kilojoules. And 151.3 and these were in joules per Kelvin. So now I can use my delta G equation. And why don't I change my H to joules this time? So now I get that my delta G equals negative 2177.4 joules. So is this process spontaneous at 325 degrees Celsius? Yes. Right, so you can see this is a process that its spontaneity depends on the conditions, because it wasn't spontaneous at standard state, but when we upped the temperature to 325 degrees Celsius, it became spontaneous. Alright, tungsten was the favored metal for light bulb filaments, in part because of its high melting point. You don't want your light bulb to melt as it's heating up. The enthalpy and entropy of fusion for tungsten are that, respectively. What is the melting point? Okay, so if you remember, so we have delta G equals delta H minus T delta S. And it asks, what is the melting point for tungsten? Well, the melting point is the temperature at which the melting process or the fusion process goes from non-spontaneous to spontaneous, or the temperature at which delta G switches from positive to negative. Okay, well, what is delta G right when it switches from positive to negative? It's 0. So I could say 0 and find the temperature when delta G is equal to 0. And if I rearrange this, get T delta S equals delta H. Now if I divide by T, I get delta S equals delta H over T. You should recognize that from the entropy problem set. Okay, we said this equation applies to a phase change, or talking about the surroundings, right? This is a phase change. So this is kind of where our delta S equals delta H over T equation comes from. But in this case, we're not solving for delta S, we're solving for T, which gives us delta H over delta S. And delta H for what process? Well, for melting. And they give us enthalpy and entropy of fusion. So just solve for my temperature is going to be my enthalpy of fusion over my entropy of fusion. Just got to make sure my units are right though, so I'm going to change this into kilojoules. And you should recognize that when I divide these, I've got Kelvin on the bottom of the bottom. It's going to flip to the top, and everything else is going to cancel. So I get 34.9, sorry, 35.4 divided by 0.0095. Okay, I'm going to do that. I get temperature equals 3695 Kelvin, but they want it in Celsius in temperature. So Celsius, I'm just going to subtract out my 273. And for Fahrenheit, I'm going to multiply by 9 over 5 and add 32. Okay, I don't need all that. 36192. I'm going to plug that all in my calculator again because the key doesn't actually have those answers on it. I want to make sure they're right. Okay, I think those are right. Okay, so again, remember that the melting point is the point at which it switches from being spontaneous, or from being non-spontaneous to spontaneous. So we set delta G equal to 0 and find T. Alright, use the thermodynamic values to predict the temperature at which hydrogen boils. So it's the exact same thing. But in this case, they don't give us delta H and delta S, so we have to find them. So what we can do is we can look up the delta H and the delta S. We're going to do products minus reactants, because we should be able to look up both of these hydrogen peroxide at liquid and gas. And we're going to use the same thing up here. Right? So eventually we're going to say, well, delta G equals delta H minus T delta S. The temperature at which it boils is going to be when delta G is equal to 0. We can range delta T equals delta H over delta S. So that's why we're trying to find delta H and delta S of the reaction. So products minus reactants is going to be delta S positive 51.7, and those units were kilojoules. I can plug these in, making sure that my units match. Kilojoules over 0.12 kilojoules per Kelvin. That gives me a temperature of about 419.3 Kelvin. That's when it's going to boil. And now, use the values in the back of the book to predict the temperature at which methanol boils. So now I'm dealing with CH3OH. Liquid goes to CH3OH gas. But I'm going to do the exact same thing as I did here. Okay, and now I can use my temperature. Now, this temperature is equal to delta S, or delta H over delta S is not always true. When is it true? It's true at equilibrium, or you could say it's true right at the threshold between spontaneous and non-spontaneous. So delta G is 0, so then we get this relationship here. Let's see. Just gotta make sure my units are the same. And I get temperature is 338 Kelvin. Awesome. How are we doing? Oh, look at us go. Just make sure it's still recording. Okay. One source of sulfuric acid aerosols in the atmosphere is acid rain is the combustion of high sulfur fuels such as coal, which release SO2 gas, and then it's further oxidized into SO3 in the air. SO3 then combines with water, forming fine droplets of sulfuric acid in the atmosphere. Use the appropriate delta G formation data in Appendix 4 to calculate delta G naught of both reactions and determine if they were spontaneous under standard conditions. So I'm going to do this as delta G. How much space do I have? Oh, I've got plenty. So I'm going to get the delta G naught of either of these reactions is going to be products minus reactants. So delta G naught to this reaction is going to be oh, they don't actually. Oh, there we go. 2 times negative 3, 71.1. So my products minus reactant is going to be 2 times. Number of pure elements, delta G of formation is going to be 0. So for the first one, delta G naught of the reaction is going to equal negative 142. That looks like it's in kilojoules. And the second one looks like alright, the second one, oh well, I guess this first one would be spontaneous because it's negative. The second one, on the key, they don't actually put the enthalpy values. Or sorry, the delta G values. So give me a second as I look them up. But I do know I'm going to have 2 times whatever the value of H2SO4 is. My reactants is going to be 2 times value, or 1 times value of SO3. And I know the value of SO3 from the first one, 371.1. Plus the value for water, which might have been in a previous. Nope, it's not. Okay, let me just look these up real quick. Bear with me. Alright, so I found the values just on a Wikipedia page. So, and I don't know why I put 2 in front of that sulfuric acid. Alright, so sulfuric acid, I got negative 6, 9.9. Actually, I don't know. Let me make sure the units on this table. Kilojoules per mole. Okay, we're good. And then water. Water as a vapor. This table says. Wow, where is it? There we go. Water is a gas. I got 228.61. So, depending on where you get those values, they might be a little bit different. But so I got delta G naught of the reaction is I could just say kilojoules. Let me plug those numbers in again, because again, it's not on the key. I just want to make sure that I'm doing it right. Alright, so this number I got, hopefully that's right. But then we could say this is also spontaneous. So what's the significance of that? Well, it means that if SO2 is in the air, it's going to spontaneously change to sulfuric acid, which is how we get acid rain. Alright, now is that other question asked? Both reactions determine if they're spontaneous. Cool. Alright, the breakdown of glucose in the cells begins with the process called glycolysis. Glycolysis is the main source of energy during anaerobic metabolism, a form of metabolism in which inhaled O2 does not play a role. Glycolysis occurs in a series of steps. One of the steps involves the conversion of fructose 6-phosphate to fructose 1,6-diphosphate. The reaction is shown below with a change in Gibbs free energy at standard conditions. So what should you notice right away? This is non-spontaneous. Okay, and yet the breakdown of glucose begins with this. Is the reaction spontaneous under standard conditions? Nope. Delta G is positive. Explain how coupling this reaction to another reaction could make the process spontaneous. Well, if we take this and combine with a very spontaneous process, then the combined delta G will be negative, and we can get both reactions to happen together. What sign of delta G would be necessary to make the overall process spontaneous? Again, negative. That's what I just mentioned. Write the inequality to determine the minimum or maximum value of delta G for the coupled reaction. Alright, so we get delta G of reaction 1 plus delta G of reaction 2 need to be less than 0. And we already know reaction 1. The 1 and 2 are irrelevant, it doesn't matter which one's which, but 17 kilojoules plus delta G of reaction 2 has to be less than 0, and therefore delta G of reaction 2 has to be less than negative 17 kilojoules. You can write the inequality to figure that out, or you can just think, well, I know this is positive 17. If I want to make the whole thing less than 0, I need a negative 17 or more. Or, well, yes, bigger number, but negative 17 or less. Would the hydrolysis of ATP occur? Would the hydrolysis of ATP, according to this reaction with delta G of negative 31 kilojoules, be sufficient to drive the conversion? Explain why. Yes, because 17 kilojoules minus 31 kilojoules, if we couple those together, is going to give me negative 14 kilojoules, which is negative. Right now, 7. Coupling of reactions can be used to make non-spontaneous reactions occur. For example, in glycolysis, some of the steps produce ATP rather than consuming it. Given the formation of ATP from ADP, according to this reaction with that delta G, so that's the same as this reaction with ADP coming from ATP, but that was spontaneous. Here, ATP is coming from ADP, so it's non-spontaneous. It's the following questions. What must the sign and magnitude be for any reaction that is coupled to this reaction to make it spontaneous? Well, the delta G of any reaction would have to be less than negative 31 kilojoules. Could the conversion of phosphoenolpyruvate to pyruvate with the delta G of negative 62 kilojoules per mole be coupled with ADP? Yes. Again, because we'd have our 31 kilojoules and we'd add our negative 62 kilojoules, and that would give us negative 31 kilojoules, which would be spontaneous because it's negative. I think that's it. All right, that's applications of free energy. Problem set 39. That's the last problem set of thermodynamics, and it's actually the last problem set of the class, so congratulations.